Hi everyone, I'm going to discuss the basic concepts of electric circuits. Electric circuits are characterized by three physical quantities. These are current, potential difference, and resistance. First, I'd like to take some time to help you understand what each of these physical quantities mean and what role they play in the functioning of an electric circuit. Imagine we start with two neutral metal plates. Each plate is filled with an equal amount of positive and negative charge. What I would like to do is establish an electric field between these plates. To do that, I will take some of the electrons sitting inside the left-hand plate and physically move them over to the right-hand plate. Doing this results in a left-hand plate that has an excess of positive charge and a right-hand plate that has an excess of negative charge. The resulting electric field between the plates can be represented both with E field lines stretching from the positive plate to the negative plate, and I can also say the two plates have different potentials. For example, let's pretend that the positive plate has a potential of plus 4 volts, the negative plate has a potential of negative 4 volts. That means I've established a potential difference, delta V, between the plates equal to 8 volts. Think about what needs to happen to move each electron over from the positive plate to the negative plate. The movement of each electron is being opposed by a force exerted by the electric field on the electron. In order to move each electron over from the positive plate to the negative plate, I have to exert a force that counteracts the force of this field. In doing this, I'm increasing the electrical potential energy of this system by doing work. The more electrons I move from the positive plate to the negative plate, the more electrical potential energy stored in this system. Now, what if I connected the negative plate to the positive plate with a conducting wire? The electrons would rush out of the negative plate and run all the way around to the positive plate, and they would keep on doing this until the whole system became electrically neutral again. Imagine I was able to cut open the circuit and microscopically observe the amount of charge passing by in a certain time t. This motivates the definition of electric current, symbolized by the letter I, as the amount of charge in coulombs passing a point in the circuit per unit time. The units of current are coulombs per second, which are also referred to as amperes, or amps for short, symbolized by the letter A. The third physical quantity that plays a role in electric circuits is resistance. It is symbolized by the letter R and has the units of ohms, written using the Greek letter omega. To understand how resistance works, we need to take a microscopic view of what is going on inside the wire. You might have heard someone say that in conductors, electrons are free to move. Well, that's only kind of true. The wire is made up of a bunch of atoms with positively charged nuclei bonded together into some sort of crystal lattice. These guys all vibrating randomly in different directions because that's what temperature is. Now, the electrons are free to move, but they have to fight their way through this vibrating crystal lattice. So their path is not completely unimpeded. They're bumping into stuff as they fight their way through this mess. Hopefully it makes sense to you that the resistance depends on the material through which it's passing and the temperature of the material, the cross-sectional area of the wire, and the path length. As the electrons pass through the wire, they naturally give up their energy to the crystal lattice in the wire. So they start off with lots of electrical potential energy, and as they pass through the wire, they lose it all, and by the time they get to the positive plate, they have lost all their electrical potential energy. So in this way, circuits are basically an energy redistribution. Someone or something has to put in energy to separate the charge, thus giving the electrons electrical potential energy, And if you then connect them around in a circuit with a wire, the electrons can give their electrical potential energy to some device that you can insert in the circuit, such as a light bulb. We represent electric circuits in the following way. So a battery is represented by two lines that are reminiscent of those parallel plates, but the longer line represents the positive side and the shorter line represents the negative side. The wires are just lines, and then a resistor is represented by that sawtooth thing over there. The battery uses some sort of chemical reaction to create a potential difference between its two ends. So far we've been talking about the electrons flowing from the negative side around to the positive side, but the convention with electric circuits is that we always say that the current flows out of the positive side around to the negative side. This is called conventional current. The next thing with electric circuits is that we assume that the wires have no resistance and that all the resistance in the circuit is located in the resistor. Now, if we want to explore the relationship between the potential difference, the current, and the resistance of the resistor, what we need to do is insert an ammeter in the circuit like so. The ammeter will measure the current, and we also need to insert a voltmeter in the circuit like so. And this voltmeter will measure the potential difference between the two sides of the resistor. It is important to note how these two elements are connected in the circuit. The ammeter is always connected in series and the voltmeter in parallel. I'd like you to think that this makes sense because an ammeter is measuring flow. The only way you're going to measure flow is to pass that flow through the ammeter. On the other hand, the voltmeter needs to be connected at two different points in the circuit because we want to compare the potential of the charges before they enter the resistor to the potential of those charges after they've passed through the resistor, thus measuring potential difference. If you now conduct an experiment where you vary the potential difference of the power source, thus affecting the current that flows through the circuit and the potential difference across the resistor, you will find that if you plot a graph of current through the resistor versus potential difference across the resistor, you will get something that is a straight line. In other words, the current and the potential difference are directly proportional. The slope of this line is equal to 1 over the resistance, and so we get an equation that relates the current through the resistor to the potential difference across the resistor and the resistance of the resistor. The current is equal to the potential difference divided by the resistance, and this is called Ohm's law. There's something very important I'd like to draw your attention to here. You'll notice I plotted current on the y-axis versus potential difference on the x-axis. There is a reason for that. Current is the dependent variable, potential difference is the independent variable. This equation is not just an equal sign, this is an equation that shows a dependency. The equal sign should be read as depends on, in the sense that current is the result of a potential difference, which is the cause of that current, and the resistance is essentially something that impedes the flow of electrons. And so basically, the bigger the resistance, the slower the current. The logic of this equation is completely analogous to Newton's second law. The acceleration is equal to the sum of the forces divided by the mass. And as you know, I like to write it this way around, again to show the basic dependency of the equation. The acceleration is caused by the force and impeded by the inertial mass of the object that you're trying to accelerate. In this way, Ohm's rule is completely analogous to Newton's second law. The last thing I want to point out is that there is an important assumption in this equation, which is that the resistance remains constant. This is not always true, however, because resistance of a wire actually depends on the temperature of the wire. And so if you were to plot a graph of current versus potential difference for something like a light bulb, you will see a graph that looks like this, basically showing that there has a low resistance when the light bulb is cold and a higher resistance when the light bulb is hot. And so this direct proportionality disappears when temperature becomes a factor.